Welcome to another edition of I Don't Think That Means What You Think It Means. In everyday life, you can look at a car on the street and know all kinds of things about it. Its position, its speed, its direction. But when you're talking about quantum objects, subatomic particles, you can't measure much about them without them being like, "F you scumbags," and then changing what they're doing completely. It's unbelievably provoking. The uncertainty principle was first proposed in 1927 by German physicist Werner Heisenberg, who was trying to figure out, with math, how to determine the exact location of an electron orbiting the nucleus of an atom. What Heisenberg discovered, again with math, is that it's impossible to know with certainty both the momentum of an electron, or any subatomic particle, and its exact position. And the more you know about one of these variables, the harder it gets to precisely measure the other one. People often confuse Heisenberg's uncertainty principle with another weird bit of quantum theory, the observer effect. This tells us that subatomic particles will act in a certain way in experiment after experiment, but once you try to observe them, essentially to measure them, they begin to act differently. Some physicists think that this has to do with how we try to measure particles, kind of like when you test the pressure in your tire. The act of checking the tire pressure with a gauge actually leaks out a tiny bit of air. In quantum physics, you can't measure jack about any subatomic particle with any precision because the act of trying to measure it makes the particle act differently. But the uncertainty principle and the observer effect are completely unrelated. The observer effect only applies to objects being directly observed. In quantum mechanics, physicists don't have to observe a particle in order to understand it within a mathematical model. What Heisenberg's uncertainty principle identifies is a fundamental property of the universe. Particles cannot have both a precise position and a precise velocity at the same time, regardless of whether they're being measured or not. This is partly because all subatomic particles exist both as particles and as waves. You've probably heard about this wave-particle duality applied to light, creating wave-like interference patterns when projected through slits, but also being detected as individual particles. All quantum objects are like that, having properties such as wavelength, like sound, but also momentum, like a car. So the more you try to treat a particle as an object, the more it starts acting like a wave. It seems paradoxical, but scientists just accept this duality without totally understanding it. Heisenberg's principle is also explained by the fact that quantum particles don't really have a specific position at any given time. Rather, they exist as what's called a cloud of probability. Within a cloud of possible positions, there's a certain probability that a particle is at each point in that cloud. In conclusion, subatomic particles are inscrutable little bastards. But like Niels Bohr, one of the fathers of quantum theory, said, anyone who is not shocked by quantum theory has not understood it. Thank you for watching this episode of I Don't Think That Means What You Think It Means. If you have other ideas for things that we should tell people what they mean despite the fact that they think they mean something else, please leave those in the comments below. Also, if you have any questions or any other suggestions at all, we're available on Facebook or Twitter, or once again, down there. Bye-bye.